We've got a sector as shown, and then a segment is bounded by a chord, and the area of it is 7.2. And then we're asked to show that theta equals 0.4 plus sine theta. Well, this is going to involve writing something down then for the area of the sector and the area of the triangle and subtracting to get the area of the segment, which we know. Okay, so first up, I'm going to work out the sector area. It's actually a half r squared theta when working in radians, which we are here. I will just quickly show you where that comes from. It comes from the fact that we've got theta, sum theta, and the fraction of the circle is theta over 2 pi. And I'm timesing by pi r squared. So the pi's cancel, and you can see we're left with this half r squared theta. So in our case, it's going to be a half times 6 squared theta. It's going to be 18 theta. All right, and then let's work out the triangle area. So that is going to be a half AB sine C. I'm not going to actually label my triangle. The main thing is that it's always two sides. By the way, this is also 6 because it's a circle. Two sides and then the angle in between that you do sine of. So it's going to be a half times 6 squared times sine theta, which is going to become 18 sine theta. And we're nearly there then, so it must be that 18 theta minus 18 sine theta is equal to this 7.2. And I'm going to divide 7.2, or I'm going to divide through by 18 now, which gives us 0.4. So theta equals 0.4 plus sine theta as required. Okay, quite a few steps to do, but hopefully you're happy with that. Next up, we're asked to let f of theta equals 0.4 plus sine theta, so the right-hand side, and then consider the value of f dash theta when theta is 1.2. Okay, I'm just gonna do that, and then we'll worry about the rest of it. So f dash theta, differentiate 0.4, you get 0, differentiate sine, you get cos. And then when theta is 1.2, you can substitute that in. So it's going to be cos of 1.2. Which gives 0.3623. So the question is, why would this mean that we can use an iterative method based on the equation in A to converge the root, assuming 1.2 is sufficiently close to the root? Well, it all comes down to something on the new specification, which says that the iteration x n plus 1 equals g of xn. Now that is very similar to what we actually have up here. It's just we haven't turned it into an iterative formula yet. It converges to a root x equals a if, so that means that the first value that we're putting in essentially, if the derivative, the modulus of derivative is less than 1, and if x1 is sufficiently close to a. Oh, sorry, a is the actual solution, and then x1 is like our starting value if it's sufficiently close. So what the short way of answering this question for these 2 marks is like 1 mark for doing this bit, and then the second mark is to say that the modulus of f dash 1.2 is in fact less than 1. So the iteration will converge. Probably just add if 1.2 is sufficiently close to the root. Okay, there we go. Now, you might be happy with that, but I'm not quite happy with that explanation. I want to talk about it a little bit more because there's a lot going on in this iterative method. So I feel like we should talk about it. The idea behind fixed point iteration is that you set x, or in this case theta, equal to some other function, and then you look at basically the two graphs, the left-hand side and the right-hand side. So if I plot y equals x, which is the left-hand side, then it's just going to look like that. And if I plot 0. I will plot it actually quite accurately, 0.4 plus sine theta. So it's going to actually start at 0.4 and it's maybe going to, actually maybe it should be a bit further down, sorry. So I'm actually trying to find this point here. And here's the thing, when you do fixed point iteration, what you do is you put, sorry, I don't know why I haven't continued this curve actually. We might even have more points of intersection. This is only a sketch. But when you put in a value and assuming you're quite close to the root, so let's say we put it in, say, here, then you go up to it, you find your y value, and then that becomes your new x value. So you go along to where y equals x is, and then you do the same again, you put it into your function. And I'm only really talking about this very briefly here, but you actually sort of create what we call a cobweb diagram, and you converge towards your solution. And what this is getting at is if the gradient is sufficiently small, then you will converge towards it. And if it's too big, then you won't. Because if I take a slightly different diagram, I'm not gonna do the cos one here because this one does converge. But if I had a gradient that was actually quite large, like this, see this is now my function, the green function instead of the red function, then when I put it in, you you put it in and then it goes up to your function, then you go across, and actually you can immediately see it's going to diverge. But when you have a smaller function, sorry, a function with a smaller gradient, sufficiently small that is, okay, this is y equals x again, and then like that. Right, this time, just realized that they're not, well, the root is going to be 0, so, it's just to illustrate a point. But this time I'm going to put it in and it's going to go that way. And then you can see I'm going to tend towards it. That in a little nutshell, without, explaining it in great depths, is what this is talking about. Okay. So if you have a sufficiently small gradient when you are putting in a value and that value is sufficiently close to the root, then you will converge towards it. It's quite an interesting, you know, numerical idea. Like what can you, because sometimes you can rearrange equations into this form and it's like, does it work or not? And it is all to do basically with how close you are to the root and the derivative thereafter. But in this case, right, that is the answer to B. We're actually done. I'm not going to say any more on it right now. So for C, we're asked to use the iterative formula. Okay, so we're actually going to be applying that sort of cobweb idea to try a starting value of 1.2 to work out theta corrected for significant figures. So you take your equation, but then you turn it into an iterative equation. So theta n plus 1 is equal to 0.4 plus sine theta n. And we've said that theta 1 is equal to 1.2. So now I can find some more until I'm getting 4 significant figures. That's the aim. Right, there's a definite way to do this, and it is to put in your starting value first and press equals. So it's stored in the answer button, and then go 0.4 plus sine of the answer, which in this case is 1.2, and get your next iteration. So in this case, 1.33203. I'm just going to write it down to 5 figures, not necessarily 5 significant figures, but 5 figures, because I'm interested in the first 4. And then you can just keep pressing equals, and it will now put in this new value as my answer. Okay, so it's just really quick, and we can keep going, and I'm just going to cycle through them. Okay, and you can see it converging. Okay, and it's actually then converged. Now, what you have to do is write down every single one, and I'm not going to keep bringing my calculator up. I've done this already. I'm just going to write down the next few. So 3716. Okay, so you can see they're still changing. Okay, at this point, you see, look, it's not changed. So theta to four significant figures is going to be 1.382. We've used fixed point iteration to get that. And I should have said at the start, like some equations just cannot be solved exactly. This one included. So there's no, if we didn't have a theta there, if we just had a number, fine. If we didn't have a sine theta there, fine. But stick them both in and it suddenly just all comes crashing down. We have to use numerical methods, which we have done here. Now, finally, it says use a change of sign method. Lots of technical things going on in this question. Great topic because it is actually, when you think about it, most equations cannot be solved exactly. If you're doing anything these days involving solving any equations, be it physics or engineering or some other fields of science, a lot of maths even, then people are doing numerical methods, and this is just a little introduction to it. So yeah, fixed point iteration and Newton-Raphson method are two methods. So change of sign to show that theta found in part C is correct to four significant figures. Right, so what we need to do is look at our 1.382. Okay, that is what we want to show. And then the next one that comes after it to four significant figures is going to be 1.383. And then to the left, it's going to be 1.381. So I want to show, actually, I want to use the midpoint. And I want to show there's a change in sign between these two. So 1.3815, because then I'm showing that there is necessarily um, a root between these two if you can get a change of sign. And that means that we don't know where it is. Is it here? Is it here? Is it here? We don't know. But what we do know is that it's all going to converge to 1.382 to four significant figures. It's not outside. It's not going to go over here. So we can return back. I'm going to consider, remember, I'm solving theta equals 0.4 plus sine theta. I'm actually going to consider a new function that I'm going to make up, consider g of x, and it's actually going to be theta minus 0.4 minus sine theta. I always like to do this, basically get the equation that you have equal to zero. So I've rearranged, it's all the way back up here, but I've rearranged this equation by minusing 0.4, minusing sine theta. So I've got the left-hand side is equal to zero, because that's what I'm expecting for my root then. So now I'm going to substitute in these values, 1.3815, and see what I get. Okay, we get a very small negative number, minus 6.36 times 10 to the minus 4. Less than 0. So we know, right, we don't know, we know the function at this point is below the axis. This is what I'm getting at. And then 3825. Again, this should come out to be positive. I can just modify it like this. And we get 1.754 times 10 to the 4. and this is greater than 0. Okay, so we know at this point it's going to be positive. So somehow, we don't know what the function looks like, but in between it's going to go through the axis. That's the key thing, and that to four significant figures is going to be closer to 1.382 than to 1.381 or 1.383. So we just have to sort of write that down formally now. So I would say that g of x is continuous because you can sometimes get a change of sign where it just jumps without there being a root. 1 over x is a good example. It jumps from negative to positive, but there's actually no root. But because g of x is continuous, and we know that because theta is continuous and so is sine theta, okay, actually it's continuous over the interval, but also for all values of x. I'm just going to write it's continuous. And there is a sign change. I don't think I need to say between these values. It's clear. So theta equals 1.382 is correct to four significant figures. All right, I know this question's been quite long. I've tried to go into enough depth such that if you've done a bit on this topic, but you've kind of forgotten it, that it's sort of reminded you of what's going on. I feel like I didn't explain this in enough, but you could talk about it for a while with different examples. I just tried to give a little brief idea. All right. First of all, this seemed like a question on just arc length and area, and suddenly it escalated into this numerical question. But yeah, nice one.